Hi, Michael. Hi, everyone. Good morning. Welcome to week 10 of the Advanced Steel Structures course. So can you see my screen now? Okay. Thank you, Swan Yu, for confirming. So today we will be looking at design of cold formed steel sections or members subjected to bending moment. Okay. So in this section, we will learn about the section and member moment capacity for the cold formed steel open sections. And as you know, any member under bending moment, we need to check the shear capacity as well. And we have also the bearing capacity or the web crippling capacity for the cold formed steel sections. And as you know, we have combination between shear and bending, and also we have combination between bending and bearing. So we have main three capacities or behavior we need to check, which is moment and shear and bearing, and two combination between bending and shear and between bending and bearing. Okay, so this is the topics we or the parts we will look at, and we have here also the project. Have you seen the project? The project is already available under assessment. So quickly here, project 2 is now available. So you can start working on the loads and the modeling on this project. And what else here? The Spark. Have you all completed the Spark assessment or not yet? You need to complete this Spark assessment for project 1 by the weekend. Okay, because it has a due date and it will close, so you need to complete it before the weekend, the end of this weekend. Okay, so back to our slides. So if we have a look here, so we'll start now sharing the slides. Okay, here is our slides for week 10. Sorry, this lecture is lecture 10, not lecture 9. Do you see the screen now? The slide, sorry. Yeah. Do you have any question, guys, before we start our lecture? No? Okay, so today our class or our lecture will be about the design of cold formed steel members subjected to bending. Okay, this in our project or in our course referring to purlins and girts and rafter or beams. So these are the member under bending moment in our shed or our project. Okay, so what is are the design consideration for members under bending moment or for members subjected to bending moment? As you know, we have two type of consideration, or actually three, but we focus only on two. We have strength or ultimate limit states, and we have serviceability limit state. For strength limit state or ultimate limit state, we have bending capacity, shear capacity, and combination between bending and shear. So we have to check M and V, and a combination of M and V. And we have bearing or web crippling. The capacity is R or RB, bearing. Then we have a combination between the bending moment and the bearing, M and RB. And then one new steering action or one new strength check is the shear lag, but the shear lag is not in our scope for this course. So if I ask you, what is the common checks between the cold formed steel and the hot rolled steel sections? We have done all of these checks in the hot rolled steel. So actually, the design of cold formed steel and hot rolled steel has some similarities in the concepts, but what is the difference? The difference is the procedures itself has some different parameters or some different checks because of the nature of the cold formed steel different from the nature of hot rolled steel. Do you agree with that? Have you done this in the design of hot rolled steel sections? No? Yes? Okay. Thank you. Here, what is the section covering the design for bending? Section 3.3 for from Australian Standard for 600. So this is the design or the consideration for strength. We have also some serviceability considerations, which include the deflection and flange curling. Okay, so these are some serviceability requirement or serviceability checks we need to do for the cold formed steel sections. Okay, so now let's start for the strengths, our focus on the strengths. So let's start with the strengths or ultimate limit state design for bending moment. So the first check is the bending moment. So for the bending moment, similar to hot rolled steel, the design or the applied moment should satisfy two conditions in these two formulas, 3.3.11 and 2. These formulas are M asterisk should be less than or equal to phi b ms and phi b mb. Here in the cold format steel, they give like the subscript for B for bending. MS, what is MS? Do you know what is MS and what is MB? MS and MB are MS section capacity. MR is what MB, sorry, is what member capacity. So similar to before. Thanks, Michael, for confirming. So we need to link, or because we don't, it is not new thing, so we need to link or memorize what we have done before in the hot rolled steel. So phi B is the capacity reduction factor from table 1.6.3. MS is the nominal section capacity according to clause 3.3.2, and we have MB member capacity according to clause 3.3.3. Okay, so our first part of this calculation is the section capacity, nominal section moment capacity, which is in clause 3.3.2. Okay, so we have two cases for the section moment to calculate the section moment capacity for cold formed steel. The first one is based on the initiation of yielding. So this one similar to hot rolled. So based on the initiation of yielding, our section moment capacity MS is equal to Z effective multiplied by F yield, where Z effective is the effective section modulus calculated with extreme compression or tension fiber at F yield. So Z effective is the section modulus using the effective width method we discussed in the previous lectures. Okay, so this is MS, so it's quite similar to hot rolled, no new. So if you know the yield strength of the section and Z effective, so you can find MS. So this is the section moment capacity. This is the first one. The second one, or the second method, is based on inelastic reserve capacity. For cold formed steel section, due to their post-buckling behavior, in some cases they can have or they can generate more capacity after buckling. So for cold formed steel section, we have something they call in the standard inelastic reserve capacity. This in some cases, the post-buckling behavior or the cold formed steel section after the post-buckling behavior, they can have or generate more strength after buckling. Okay, so this method has some limitation to use or some conditions to be achieved. This is just to know, not to use in our calculation, but because we have two cases in the standard, so based on your design and these conditions, you can consider this condition. Okay, so quickly, what is the conditions? The member is not subjected to twisting or lateral or torsional or distortional or flexural buckling. So the member will not be under any of this buckling behavior. The effect of cold forming is not including in determining the yield strength, because do you remember what happened to the yield strength for cold formed section due to cold formation or due to the cold form process? Do you know? Remember before we have this is our typical stress strain curve for steel. So the green one is for what? For hot rolled section. So this is a normal one. So after cold formation, due to the cold formation, we need to apply, if you remember, we need to have deformation or permanent deformation on the section. So that's why the red curve is the curve for, or maybe a little bit higher, sorry, for cold rolled or cold formed steel. So this for hot rolled steel. and this for cold formed steel. So what does the standard mean here? The effect of cold formed not considered. The design shear force doesn't exceed 0.6 F yield times the area, the web area, D1, T1, TW. The angle between any web and the perpendicular to the flange doesn't exceed 30%. So this all cases you need to fulfill before using the elastic reserve capacity. So this case is a little bit ideal, so we can't use. So we will be using the formula we used here. The section capacity is equal to ZE or Z effective times F yield. And in general, the standard limit the capacity, the nominal section capacity, MS, to be either 1.25 ZE, 1.25 ZEF yield, or that causing maximum compression strain of CY EY. So the maximum based on this one here, MS cannot exceed or should be less than or equal to 1.25 Z effective F yield. What this mean? The maximum increase in our section capacity using the normal or the yield calculation is only 25% more than the actual one. Okay, so the inelastic reservoir capacity is limited to 1.25, the value from the elastic capacity. Okay, a quick example here about the calculation. So the section moment capacity for this C section, 150/12 section. So using the initiation of yielding clause, MS equal to Z effective times F yield. From the table, Z effective of this section is 11.76 times 10 to the power 3 times F yield, for example, 500 MPa for this type of section. So the section capacity is 5.88 kilonewton meter. So the section capacity is straightforward because no global or no overall buckling behavior for the member. What is the second capacity or the second uh, check we need to do for the member under bending, for the bending capacity? The member moment capacity. The member moment capacity is covered by this clause 3.3.3 nominal moment, member moment capacity. For the member moment capacity, we have three cases or three possible considerations. For the member under bending, again, the member nominal capacity is concerned with or considering what overall, just something you learned in the hot roll. So overall or global buckling behavior. So for the global buckling behavior in cold formed steel, we can have three cases. The first case is member subjected to lateral buckling. So a member subjected to lateral buckling, this is our first case, which is covered by clause 3.3.3.2. And second case, we have member subjected to distortional buckling. So we can have lateral buckling or distortional buckling, and we will see now what is the difference between both. The third case is for channels or Z section with one flange fastened to sheeting. So this case for purlins and girts. because the Berlin and the girth is fastened to the roof sheeting, right? So this is a different case. So for this case, we have clause 3.3.3.4 covering it. So in the member capacity, we need to consider whatever applicable from these three cases, and that's why the standard mention or limited the member moment capacity by the following two statements. MB will be the lesser of MS and the values calculated according with 3.3.2 and 3.3.3. So MB is equal to the lesser of MS and MB from the case 1, this case, or this case. MB 3.3.2 and 3.3.3.3. This one case. Or if it is Berlin like this, so MB equal to the lesser of, again, MS and MB from clause 3.3.3.4 or 3.3.3.3. So this is the cases for the global buckling behavior, and let's now start looking at one by one. So for member subjected to lateral buckling covered by clause 3.3.3. What is the lateral buckling means? The lateral buckling or flexural torsional buckling. Lateral buckling or flexural buckling. When you apply moment to this beam, what happened to the beam? If you look to here, so the beam has buckled laterally, as you can see here. So this is the original beam, and then this is our beam after buckling. Okay, so this is what we call lateral buckling. This lateral buckling will happen when the beam is restrained at this point and restrained at this point and free to buckle between the two points. So we have restraint here and restraint here, and the beam itself has the freedom to move laterally in the middle between the two. So this is type of buckling occur in the member subjected to bending moment like this. So this is our first case. So what is the member capacity for the member subjected to lateral buckling? If you like, if you ensure that the member, your beam will be subjected to bending, subjected to lateral buckling due to bending, so you need to follow clause 3.3.3.2. So under 3.3.2, we have two cases. The first case for open section members, and another case for closed section. So our focus only in this course will be about open section. Open sections like C section or Z section or even double C section. Any section that it is open, so covered by this clause. Closed section or box section like something like square hollow section or rectangular hollow section. So these are closed section. So these are open sections and these are closed sections. So in this case, The formula is, so these are the section example. So C, double C, and Z section. So the section member capacity, or the member capacity for this member for laterally unbraced segment of singly or doubly or point symmetric section subjected to lateral buckling shall be calculated as MB equal to ZC FC, where ZC is the effective section modulus calculated at stress FC in the extreme compression fiber. So how to find FC, or the the critical stress? So it is equal to MC divided by ZF. So we have FC equal to MC, the critical moment, divided by ZF. Where MC is the critical moment, we will see how to find it now. And ZF is the full unreduced section modulus for the extreme compression fiber. So ZF is equal to Zx, or the full section modulus, from the capacity table. So no reduction in Z in this case. So if we know ZF and MC, we can find FC, and then we will need to find ZC. But let's start first with how to find MC. So how to find ZF is already given in the table, so no problem with ZF. So our target firstly is how to find the critical moment for lateral torsional or lateral buckling. Okay, so the critical moment MC will be using this clauses. We have three cases based on lambda b, or the buckling factor, cylinder necessary factor. So MC can be equal to My, or the yield moment, if lambda b less than 0.6. So how to start this calculation? Our target firstly is lambda b. So we need to find lambda b first to decide how much is MC. Okay, so lambda b is non-dimensional slenderness ratio. So in all our calculation in hot rolled and cold formed steel, lambda is slenderness ratio. Used to determine MC for members subjected to lateral buckling. What is the formula for lambda b? Lambda b is using this formula. So lambda b is equal to root M yield divided by MO. So again, we need to find other parameter to finalize this calculation. So we need MO and MY, or M yield and MO. M yield, or MY, is the moment causing initial yielding at the extreme compression fiber of the fall section. What does this mean? This means that M yield is equal to ZF times F yield. So this one is simple. So My is equal to the full section capacity ZF from table multiplied by F yield. So we know already ZF from the table, and F yield is the section modulus. Sorry, ZF is section modulus from table, and F yield is the yield strength. So our issue, or our main calculation, will be for what? For MO. MO is the elastic buckling moment determined in accordance with rational elastic buckling analysis or paragraph 2D 2.2. So MO will be calculated using this section here, D 2.1 Appendix D. So if we go to the standard in Appendix D, so this is how to find MO. So MO from Appendix D is using this formula here, or clause D 2.1.11. So again, we are looking at single symmetric section. Axis is the axis of symmetry. Okay, so for single symmetric section bent about the symmetry axis or x axis in our case, and for doubly symmetric section bent about x axis, and for z section bent about axis perpendicular to the web or x axis again. So MO is using this formula, where the elastic buckling stresses FOY and FOZ are defined in paragraph D 1.1. So if you look to MO, we have CB and AG and RO1 and root FOY and FOZ. AG is the section area or gross section area, so no problem with AG. We'll see now. RO1 is radius of or RO1 is coming now. RO1 is the polar radius of gyration. So R generally is radius of gyration, but this is a polar radius of gyration about the shear center. So these two will be found using the capacity tables. So they are already calculated in the capacity table, so no problem with that. So our main targets will be to complete this calculation. We need to know CB, FOY, and FOZ. So what is FOY and FOZ first? FOY is the elastic buckling stress in an axially loaded compression member for flexural buckling about the buckling about y-axis. So FOY is the elastic buckling stress for axially loaded compression member or any member under compression, like because the bending moment will cause also compression in parts of the section. So this is the elastic buckling stress for buckling or flexure buckling about y-axis. This is the main thing we need to know. So FOY is buckling stress for flexural buckling about y-axis. So that's why it is FOY. So FOY will be found using the formula, as you can see, pi squared EIY average divided by A gross times L effective Y squared. This includes the 1.1.2.4. For FOZ, what is FOZ? The definition of FOZ is elastic buckling stress in an axial load compression member for torsional buckling. So again, FOZ is buckling stress for torsional buckling because buckling stress for torsional buckling because the buckling happen or occur around z axis. So if you have a section, if we have a section like this, so we have if this x-axis and this is y-axis for the section, so the longitudinal or the vertical axis is what? Z-axis. So any buckling or any moment around Z is what? Is torsional or torsional moment. Okay, so that's why FOZ is the elastic buckling for torsional buckling. Elastic buckling stress for torsional buckling. The definition of this buckling stress is using this formula here. So we have FOZ equal to J average divided by A gross times RO squared average multiplied by 1 plus pi squared IW net divided by J average LEZ squared, or enclosed D 1.1.25. So our main calculation for MO will be the two values FOY and FOZ, where this is the parameters. AG is the gross sectional area or the full cross sectional area. RO1 is the polar radius of gyration for the cross section about the shear center. Again, if we look to the cross section of the channels, we have here is the CG, somewhere here, and we have another center which is somewhere here, which we call shear center of the channel. So the shear center is because if you apply any vertical load or concentrated load here, this section will be under moment. So the shear center is when you apply the load here, the load will be applied without adding moment to the section, moment on the section. So this is the importance of the shear center. If you apply the load here, let's make it with a highlight here. So this load will cause additional moment on the section because the section geometry cause that the section will cause moment. This moment will be the distance from here to here. So M equal to, if this B times E. So any section we apply the load on the flange, not on the shear center, will be under two things: moment and axial load. But if you apply the moment, the load at the shear center, like this one here, so the moment will be 0. Okay, so this is the importance of the shear center for this section. Okay, so let's go again. So RO1 is the radius of gyration for the cross section about the shear center. It is calculated using this formula here. So RO1 equal to the square root of Rx squared, Ry squared, XO squared plus Y squared, where Rx and Ry are the radii of gyration of the cross section about X and Y axis. XO and YO are the coordinates of the shear center of the cross section. All these are section probabilities that can be found in capacity tables. So for the available sections in the market, you don't need to find these values because they are already uh, calculated or are already available in the tables. Okay, and even this one RO one itself are given in the table. But this how the tables calculate this value. Okay, so this for RO. If we go back, what else we need to find? CB. CB is a coefficient depending on the moment distribution on the laterally unbraced segment. So CB is equal to 12.5 mmx divided by 2.5 mmx plus 3 m3, 4 m4, and 3 m5. So this is our formula for CB. Have you seen something like this before? We have similar value for hot rolled sections for the moment distribution on the segments, where mmx is the absolute value of the maximum moment of the unbraced segment. So for example, if you have a segment like this, so mmx is the maximum value here. M3 is the absolute value of the moment at the quarter point of the unbraced segment. So you need to have 4 quarters. So we have L over 4 over 4, L over 4, L over 4. So we need the moment here and here. So M3 is the moment at the first quarter. M4 is the absolute value at the moment of the unbraced. So here we have M2, or sorry, M4 is equal to M max. M5 is the absolute value of the moment at 3 quarters. So if this M3, so this is M5. So CB will be using this formula, or the coefficient depend on the moment distribution, or the standard give us another option. So for simplification, CB may be taken as unity for all cases. So you can take CB as 1 as well. For any case, you can take CB as 1. For cantilevers or overhangs where the free end is unbraced, CB shall be also taken as 1. So CB has 3 options. First option is using this formula, this option 1. Option 2 is CB equal to 1. Option 3 is from table 2.1. So table 2.1 is option 3. So table 2.1 is coefficient CB for simply supported single span beams with uniformly distributed load within the span. Okay, so for this case, if you have a simply supported beam with uniformly distributed load within the span, you can use the table. Okay, do you have any question, guys, up to here? So if we summarize this one now, for the member under lateral buckling, all this calculation was to find what MEB. MEB equal to ZC times FC. All our problem is how to find FC. So to find FC, we need MC divided by ZF. ZF is the full unreduced section modulus. We know from the table, so no problem. So our main target is how to find MC. So for this calculation, our target is MC. How to find MC? To find MC, we need to find lambda b first. Then we decide which case to select for MC. So lambda b, we need to find my and mo. My is simple, so we have ZF field, so we need to find my. We can find my easily. So our target again, second target is mo. So mo is equal to this formula here. CB age gross RO1 root FOY FOZ. So to find MO, we need CB, A gross, RO, FOY, FOZ. So A FOZ using this formula here, pi squared E, IY average, A gross, LEY squared, FOZ equal to G, J average, A gross, RO 1 squared average, times 1 plus by EI warping divided by G divided by multiplied by J average LEZ all squared. So if we find these two, we need now to find what? RO1 from this formula or from the table and CB. CB can be taken as 1. So if we know CB and A gross and RO1 and FOY and FOZ, we can find MO. And then using MO, we can find lambda B. Using lambda B, we will decide which case to find MC. So for example, if it is between zero point 0.6 and just an example, if it is in somewhere here, let's say lambda B is equal to 1, for example. So we need to use this formula to find MC. So 1.11 my multiplied by 1 minus 10 lambda b squared divided by 36. So if we know lambda b, we know MC. If we know MC, we go back one more step to find what? FC. If we know FC, we can easily find MB. Okay? So do you understand this part? So the calculation is a little bit complicated or there are a lot of parameters, but there's if you know the procedure, so it is straightforward procedure. Okay. Do you have any question now? For now? Okay. Do you want to have some break? 10 minutes break, then we can continue. All good? Okay. So I will see you at maybe 10:15. Okay. So about 13 minutes. So see you after 13 minutes, guys. Thank you. Okay, guys. So let's continue. Thanks, Michael. Thanks, everyone. So the second case of the member capacity or member moment capacity is for members subjected to distortional buckling. The members subjected to distortional buckling are covered by clause 3.3.3. Okay, so let's have a look on what is the distortional buckling. The distortional buckling may occur in cross sections that are braced against lateral and flexural torsional buckling. So if you remember the first case, the members were laterally unrestrained. So if you remember this diagram here, okay. So this diagram was for the lateral buckling. So if we have support here, for example, and support here, so as I told you, in the other case, the two the two supports here were restrained against lateral buckling, but any point in the middle was free to move laterally. Okay, so this case of the lateral or the flexural buckling. Okay, but for the distortional buckling means the beam along the beam is not free to translate. So translation is not allowed. So in the flexure under flexure, the beam, the long of the beam, it is not free to move laterally. But due to the applied load, the distortional buckling will happen means, as you can see here, if we move this parts, the flange can rotate, and if the flange rotate, so the web also will need to rotate. And because it is fixed at the bottom, for example, so this is the buckling shape we call distortional buckling. Okay, so this is our original beam. So as you can see, no lateral movement happened. So that's why you cannot call it lateral buckling. Okay, this distortional buckling usually happen or mainly happen in the libbed sections. Because as you know, we have two type of section. So we can have libbed section or unlibbed section. So here, unlibbed section means section without lib. Here, libbed section or with lib. So the distortional buckling is likely to happen for the libbed section. So distortional buckling likely to occur for this section. And as we discussed, this beam will go down, this flange will go down like that. So this web will go outside, and this will be the distorted shape. Okay, for this one, distortional buckling not likely to happen or unlikely. to occur. Okay, so this is the shape of the distortional buckling. Now, what is the formula to design section under distortional buckling or subjected to distortional buckling? So again, we have clause 3.3 covering the member under distortional buckling. So the formula, same formula to before, MB equal to ZC times FC. So MB and ZC and FC are the critical stress of the compression extreme compression fibers, similar to before. So how can we find FC and ZC in this case? So the standard again give us the formula for ZC and FC. So FC, where distortional buckling involves rotation of the flange and lip about the flange junction of a channel or Z section. ZC is the full section modulus, except that when K phi as given in equation 2.2.1 is negative, then ZC is the effective section modulus calculated at stress FC. So if the distortional buckling involves rotation of the flange and lip about the flange, you can take ZC as ZF. So ZC in this case can be taken as the full section modulus. So this for ZC. And we'll see this in the examples because it depends on the case of your beam. And FC, similar to before the first case. So FC again equal to MC, the critical moment, divided by ZF. So the difference is what is MC in this case and what is MC in the lateral buckling case. So each the symbols or the parameter are same, but how to find them, this is the difference. So FC here again MC over ZF, where ZF is the full section modulus from the table. So no problem with ZF. So the problem or how now our issue to find MC. So the MC is the critical moment. Again, it depends on the slenderness ratio lambda d. Here in this case, how many cases for MC we have? Two. If lambda d, the slenderness ratio. So again, lambda is the slenderness ratio for distortional buckling. So depend on lambda d, you can find MC using this formula or this formula. So MC equal to My or MC equal to My divided by lambda d times 1 minus 0.22 divided by lambda d. So this case for when distortional buckling involves rotation of the flange. Second case or case B, where distortional buckling involves transverse bending of the vertical web with lateral displacement of the compression flange ZC. So this will happen in the compression member. As you can see here for the flexure member, no translation happened, and this point here is what the standard call the web flange juncture. So this part is the juncture between the web and the flange. So this means that case A is related to this part here. So this case A, and case B here, distortional buckling involves transverse bending of the vertical web with lateral displacement of the compression flange. So as you can see, we have a little bit of translation here, so this can be case B. So based on the case you are calculating, so you can find the values of MC and ZC as follows. So ZC in this case is the effective section modulus, not the full section modulus. So here ZC equal to ZE. And for the critical moment in this case, not only two cases, we have three cases. So again, based on what? Lambda D. So we need to find lambda D. Lambda D less than 0.59, so equal to M yield, more than 1.7 M yield multiplied by 1 over lambda D squared. And in between, it will be My multiplied by 0.59 divided by lambda D, where My again is the moment causing initial yielding. Do you remember how we find that? My again equal to ZF times F yield. Lambda D is a non-dimensional structure cylinderness ratio used to determine MC for members subject to distortional buckling, where lambda D equal to M yield divided by MOD. So we have lambda D equal to M yield divided by MOD. So M yield, okay. MOD is the elastic buckling moment in the distortional buckling mode. So MOD is equal to ZF times FOD. So we have MOD equal to Z full section modulus multiplied by FOD, where FOD is our target now, the elastic buckling stress, or the elastic distortional buckling stress determined in accordance with a rational elastic buckling or paragraph 2D2.2. So FOD, again, elastic buckling for distortional buckling. Elastic buckling stress for distortional buckling mode. Using paragraph 2.2. Okay, so FOD is equal to E divided by 2A multiplied by alpha 1, alpha 2 minus root alpha 1 plus alpha 2 all square minus 4 alpha 3. E and A is the Young's modulus and cross-sectional area. So to find FOD, you need alpha 1, alpha 2, and alpha 3. Three parameters. Where alpha 1 using this formula, alpha 2 using this formula, alpha 3 using this formula, and lambda in this case, because I just put this one for you here, because the formulas, all these formula are similar for flexure member and compression member. because the distortional stress can happen for member under bending moment and member under compression. The only difference is this parameter here. So the only difference in the calculation is lambda. So only for flexural or member under flexion. So here to find the value of FOD, you need alpha 1, alpha 2, and alpha 3. And as you can see in this parameter here, we need lambda. Lambda in this case, for the flexural members, lambda is equal to this formula or coming from this formula here. So 4.8 multiplied by Ix, B flange square, B web divided by 2, T cubed, all to the power 0.25. Okay, so let's summarize this part here for the distortional buckling. So for the distortion buckling, to find MB, you need ZC and FC. ZC is okay, either case A, so ZF, or ZE if it is case B. So if you know ZF or ZE, so ZC is okay. Then we need to find FC. FC is equal to MC divided by ZF. No problem with ZF, so the problem is MC. MC can be in case A, depending on these values here, lambda D, one of these. So if you know MC, you can find FC, then you can find MB. The other option, if it is a compression member or if there is transverse bending and lateral displacement, so we need to find lambda d using this or compare lambda d to these formulas to find MC. To find lambda d, we need my and mod. So we know my already, but mod we need FOD. FOD, we need to go to this formula here, including alpha 1 and alpha 2 and alpha 3. So to find alpha 1 and alpha 1 especially, alpha 1 need lambda. Lambda equal to this formula here. So if we know lambda, we can find FOD, we can find lambda D, so we can decide which MC. If we know MC, we can find MB. So this is the member capacity for members under distortional buckling. So the third condition for the member capacity is members with one flange fastened through to the sheeting, which means especially purlins and girts. This is covered by clause 3.3.3.4. So in this case, as you know, the purlin or the C-section, the purlin is fastened to the roof sheeting. So the roof sheeting give it some restraint, so the behavior is different. So if this our section, so this is our purlin and this is our roof sheeting in this case. So the design of this beam or this purlin is covered using section or clause 3.3.3.4 because the buckling behavior for this case will be different. So for beams having one flange through fastened to sheeting, the nominal member capacity, moment capacity, MB, of a channel or Z section loaded in plane parallel to the web with the tension flange attached to sheeting with the compression flange laterally unbraced shall be calculated as follows. Okay, so as you can see, which flange is attached to the sheeting here? The standard mention which flange attached to the sheeting. Can you see it? The tension flange attached to sheeting, and the compression flange laterally unbraced. So this is the case we are looking at. So this means that the moment on this beam in this case is our moment in this case. So this means that the top flange now is our tension flange or compression flange, guys. This is our tension flange. And here, this is our compression flange. So compression flange unbraced. When this can happen, do you know? Can this case happen? Happened? I ask you this question. If we have this Berlin running here, so if this our Berlin, in the wind case, when the wind case, upward, uplift. So in some cases we have the wind, uplift wind. So in case of uplift wind, how the moment will look like? This is how the moment will look like. Right? So this is our maximum moment. Okay? So if we look to our flange here, or our section here, sorry, our Berlin here. So this Berlin will be under moment like this. So the top flange connected to the sheeting is our tension flange. The bottom flange in this case is our compression flange. Okay, so this is the case the standard refer to. So MB in this case, as you can see, MB equal to R times Z effective multiplied by F yield. So this similar to what? The section capacity. So this part, if you go back to our first part of the bending, the yellow part here is our section capacity. So it is the section capacity multiplied by what? A factor R. So the new part is R, where R is a reduction factor. So it will be the section capacity multiplied by a reduction factor R. This reduction factor varies between 0.6 and 1, depending on the bridging level of the burn. ZE, again, is the effective section modulus calculated with the extreme fibers, extreme compression fibers is F yield. There is a note here that the manufacturer's capacity or load tables for boiler and girls would usually have been developed using tests. Hence, this cause is unlikely to be used very often. So that's why if you go back to our assessment in reality, in Berlin's and girls, we can use the capacity table directly to select the section. So no need to calculate R and ZE and F yield for the Berlin because the capacity table give us directly if you have a certain span, what is the maximum load that can be carried by this Berlin. So based on the type of or the value of load you have, you can select the proper Berlin. But anyway, this is the values of R based on the standard quickly. So we will not use it in our course, but for your information or for background, R has two cases for uplift loading, for continuous lapped Berlins with three or more spans using Z section. So may I quickly open the capacity table for you? Okay, guys, can you see the Berlin capacity table now? Okay, so for the capacity table for Berlin, this is the shape of the Z and C sections, and this is the probabilities, and this is the bridging system for the Berlins, for example. I just want to show you something here. So this is a Berlin, for example, but single span. Okay, so as you can see here in this diagram here, so we have to connect the Berlin together. We have overlapping, and we have, as you can see here, this is one Berlin from the left, from the right, and one Berlin from the left, and we have to overlap the two Berlin. Okay, so this we what we call is overlapping. So we have bridging and overlapping, and all of this affecting our capacity for the Berlin. Okay, so the capacity table give us directly, if you look here, so the capacity table give us the limit state capacity for the Berlins for each section. So for example, this for section 110. So based on how many bridges, how many bridging, what is the bridging number, and the span of the Berlin can give you the maximum inward or outward load. So inward means loads downward, because this is what you will need to do in your report. So you calculate the wind uplift and or inward and upward or outward. So, for example, if your span is 3 meter, the Berlin span is 3 meter. So, if you have inward load, what is the maximum load you can carry by this Berlin? 1.95. So, if the load applied to your Berlin is 1.5 or something, so this section is okay. But for example, if it is 3, so you need to go to a bigger section. Okay, so this for inward. For outward, so the problem of bridging or the bridging will help the upward loading. So for upward loading, the bridging affect our calculation. So affected by bridging. Okay, so the N word, no effect for the bridging in some cases, but in some cases it has also effect, but the effect is more critical for the upward. So for the outward, you need also to check if you have zero bridging or one bridging or two bridging. So if you have this band again, so if you have zero bridging, the maximum load is 1.01. If you have three bridging, so you have 1.95. So based on your assumption or for your selection, you can select the possible cross section. So if we go back to our slides, so for uplift loading, for continuous slab purlins, so also you have two cases. We have single span and continuous or overlapping. So you also need to select the Berlin according. Yeah, you can assume whatever you want in your project. If it is not mentioned, so you can assume either single span or continuous or overlapping. So R will be according to the number of bridging. So if you have no bridging, so bridging is 0. So how much is R? 0.75. If you have one row of bridging in end and interior span, 0.85. Two rows of bridging in end span and one or more rows, so 0.95. Two rows of bridging, so no reduction. Okay, so the factor R is based on your assumption for the project or for the design. Okay, do you have any question about this part? So in the Berlin for the project, you don't need to, this what is the instruction mentioned, you don't need to calculate the beam, the moment, the member moment capacity using this formula because we will be using the capacity table directly. But for the rafter, you need to go through the standard formulas. Okay, so this only for Berlin and Gertz. The second case here for downward loading. So if you have downward loading, that's why the bridging is not as effective or as effective as in the upward. For continuous lapped Berlins with three or more span using Z section without bridging or any other configuration, R shall be equal to 0.85. Okay. The reduction factor R shall be limited to roof and wall system conforming to the following. So the standard give us some limitation or some condition need to be satisfied to use the factor R. So R is only used for if the roof and the wall system conforming with the following. Member depth shall not be more than 300 millimeter. Flange shall be edged stiffened compression elements with the lip perpendicular to the stiffened flange. Depth to thickness is between 75 and 135. Depth to flange width between 2.3 and 3.2, and all these conditions. Member span length shall not be more than 10.5. For continuous span system, the longest member span shall not be more than 20% greater than the shortest span. So this means L long for the beam, for the Berlin, less than or equal to 1.2, the shortest or the less span. So these are all conditions need to be used or need to be available to satisfy the condition. The next part is the shear capacity of the webs. For the shear capacity of the web, this is using clause or section 3.3.4 in the Australian standard for 600. So the shear capacity of the webs. As you can see here, this is a typical shear failure of the cold formed steel section. So the buckling here, this is how the buckling happen. So if it is simply supported edge or fixed edge. So if simply supported edge means the web, and also again, where is the shear failure happen? So the shear failure in the webs. So as you know, from the hot rolled steel, the webs are the element that resist the shear. So this is a typical shear failure, and this is two cases. If it is simply supported or fixed support, so the buckling will be different, a little bit different. So the width of the buckling wave in the simply supported is 1.33 times the height. H is the height of the web. For the fixed, it is 0.8 times the web height. So this is how frequently the buckling wave will occur. Okay, so this figures or the shapes are just some like indication how the buckling shape and the shear failure of the beams in the cold format section. So in section 3.3.4, the shear capacity. So again, shear capacity of the web. So shear capacity of webs without holes, this is our focus. We are not considering holes in our beams. So the design shear force, V asterisk, shall be or need to satisfy this condition. So V asterisk should be less than or equal to phi V times VV, where phi V is the reduction factor for what? For shear from table 1.6.3. So this is a reduction factor, and VV is the nominal shear capacity of the web. Okay, here it is quite similar to before in the hot rolled steel. So we have three cases for VV in this cold formed steel design. So VV will be according to the percentage D1 over TW. So to decide which formula to use, we need D1 over TW. D1 is the web height, clear web height. TW is the web thickness. And we need to compare to this ratios here, which is E multiplied by KV divided by F yield. So this are the limits, the root, and 1.45 times this root. So if D1 over TW less than this value, so we use this case, and this is the maximum shear capacity for, so this is the biggest one, and this is the value if it is between the two values, and this is the values if it is more than the limit 1.45 415 the root. So the parameters are easy. If y is the yield stress, d1 is the web height, tw is the web thickness. Again, here is the same. Kv, what is Kv? Is the buckling coefficient. So Tw, everything is known for us. So the only thing is how much is Kv, or what is the cases for Kv. So the parameters for the formulas are dW, d1 is the depth of the flat portion of the web measured along the plane of the web. So if this our section, so the height of this part is our T1, D1. TW is the web thickness. KV is the shear buckling coefficient determined as follows. So KV is our shear buckling coefficient for unstiffened web. You can take KV as 5.34. So KV equal to 5.34 for unstiffened web. Unstiffened web means no stiffeners. So if you don't have stiffeners, so you can take KV as 5.33, 0.34, sorry. For stiffened web, or for beams with transverse stiffeners, so we have two cases for KV based on the spacing of the stiffener. So A is the stiffener spacing. So A is the stiffener spacing, as you can see in this diagram here, and D1 is the web height. So according to that, if we have A over D1 less than 1, so you can use KV equal to this formula here. 4 plus 5.34 divided by A over D1 all square. And if it is more than 1, so it is 5.34 plus 4 divided by A over D1 all square, where A is the shear panel length for unstiffened web, in this case here. So this is our shear panel, or distance between transverse stiffener for stiffened web elements. So for shear, it is simple calculation, not too much calculation needed. To find, to check the shear, you need to find phi and VV. VV according to the three cases, according to the limit. So you need to find the value D1 over TW compared to the limit. So everything known except for the value KV. So the value KV here and here is the buckling shear coefficient, or shear buckling coefficient. So KV has three options or three cases. It can be for 5.34 for unstiffened web, and it can be 4 plus something or 534 plus something if it is more less than 1 or if it is more than 1. Okay, so if we know VV, we need to go to find phi and then compare to V asterisk to find the, or to check the shear. Okay, do you have any question, guys, for this part? So we'll stop here now, and we'll see you in the class soon. Any question before we leave? No? Any question? Binhua, Rahmat, Jihao? No question? Okay, guys, thank you for attending today, and I will see you in the class. Bye.